Hello my friends and welcome back to the You Can Do TV channel. The automatic H-beam production line is designed to optimize the manufacturing process of heavy steel structures, particularly focusing on H-shaped steel beams. By minimizing reliance on manual labor and traveling cranes, this production line maximizes efficiency and throughput. The process begins with cutting and laying off the raw materials required specifications, ensuring precision and uniformity in size. Components are then assembled into T-beams, integral parts of the H-shaped steel structure. Hydraulic mechanisms are employed to flip the assembled T-beams by 180 degrees, facilitating subsequent steps in the production process. The T-beams are then arranged and welded together to form the characteristic H-shape, the primary product of the production line. Another hydraulic overturning maneuver repositions the H-beam, preparing it for further processing. Automated shifting mechanisms transport the H-beam to the next station in the production line, ensuring a smooth flow of work. Sequential welding of multiple seams ensures structural integrity and strength of the H-beam. Controlled by a chain mechanism, the H-beam is rotated at specific angles to facilitate welding and manipulation during the production process. Roller systems are utilized to feed the H-beam into position for various operations, ensuring precise alignment and movement. Hydraulic systems are employed to straighten any deformities or imperfections in the welded plates, ensuring quality and compliance with specifications. Finally, the finished H-beam is conveyed out of the production line, ready for further processing or assembly into larger structures. Throughout the entire process, automation plays a key role, reducing the need for manual intervention and enhancing efficiency. Conveyor rollers, hydraulic mechanisms, and chain systems work in harmony to transport, manipulate, and assemble the steel components, resulting in a streamlined and optimized production line for H-shaped steel structures. The TDRi aluminum boat welding system is a highly efficient and precise automated welding solution designed specifically for aluminum boat manufacturing. Here's how it works. Offline programming. The system utilizes Robotic's offline programming software, allowing the welding program to be prepared in advance. This minimizes downtime in the welding cell when switching between products. The offline programming saves valuable time for the customer and enhances production efficiency by up to 50% compared to manual welding setups. Seam finding and following. Integrated with a seam finding and following camera system, the system accurately locates and follows the seam of the aluminum boat hull. This ensures precise welding along the desired path without the need for manual adjustments. SPN 83000 Positioner and SPG 300 HD Gantry. The system includes TDRi's own positioner and gantry, which provide optimal access and positioning for welding. This setup allows for the best possible weld positions, ensuring high-quality welds throughout the boat construction process. Laser seam tracking. Integrated with a laser seam tracking system, the welding cell compensates for any deviations in the weld path. This ensures consistent weld quality, even in cases where the material or seam may vary slightly. SGP 300 HD Heavy-Duty Pillar Gantry. This series of pillar gantries provides robust support for the welding process, with a large payload capacity of up to 300 kilograms. It is suitable for various applications, including twin-wire welding, laser cutting, plasma cutting, and more. Robotic heavy welding for heavy construction equipment involves employing advanced techniques and specialized equipment to ensure precise and efficient welding of various components used in construction machinery. Intercro, a prominent player in this field, utilizes torch changing, preheating, single wire, and tandem, twin welding techniques to enhance the quality and durability of products such as truck-mounted cranes, aerial working platforms, loaders, and tree transplanters. Key to the success of robotic heavy welding is the accurate positioning of both the robot and the workpiece. Intercro employs various tools like single or multi-axis workpiece positioners, sliders, pillars, and gantry systems to achieve this precision according to industry standards. Additionally, technologies like arc, touch, and laser sensors are utilized simultaneously to ensure flawless welding applications and achieve precise results. Some projects undertaken by this robotic heavy welding include welding excavator buckets, crane components, forklift parts, and various other heavy machinery components such as mobile cranes, towers, firefighting equipment, and silos for fuels and chemicals. Spot welding robots in the automotive industry are integral for joining metal components quickly and precisely. These robots are equipped with specialized arms that hold electrodes, which deliver an electrical current to create a weld. The process involves the robot positioning the electrodes precisely over the metal pieces to be joined, applying pressure, and then delivering a burst of electricity to create the weld. To ensure accuracy, spot welding robots often utilize advanced sensors and vision systems to detect the exact location of the weld points and adjust accordingly. Additionally, they can be programmed to perform a variety of welds on different types of metal, making them versatile for various manufacturing needs. Welding stands as a cornerstone process in numerous manufacturing sectors, from automotive to aerospace, construction to shipbuilding. However, despite its critical role, traditional welding methods often entail significant time investments and labor-intensive workflows. This inefficiency can bottleneck production timelines and inflate operational costs. Enter welding automation, a paradigm shift that promises to revolutionize the landscape of manufacturing efficiency. At its core, welding automation entails the integration of advanced technologies to mechanize various aspects of the welding process. This can encompass a spectrum of solutions, ranging from sophisticated robotic welding systems to purpose-built automated welding cells. The overarching goal? To streamline operations, enhance productivity, elevate weld quality, and curtail labor expenses. Consider the versatility offered by robotic welding systems. These robotic arms, equipped with welding torches and sensors, possess the agility to execute a myriad of welding tasks with pinpoint accuracy. Their programmable nature allows for precise control over welding parameters, ensuring consistency across batches and minimizing the likelihood of defects. Meanwhile, automated welding cells are tailored to specific welding applications, optimizing efficiency and throughput for designated tasks. Enterprises seeking to harness the power of welding automation often turn to seasoned experts like Mpamac. With over 5 decades of experience in designing and manufacturing welding automation solutions, Mpamac stands at the vanguard of innovation in the field. Their offerings span a comprehensive array of options, ranging from standalone equipment to fully integrated production lines. Each solution is meticulously crafted to uphold stringent safety standards, enhance ergonomic comfort, and deliver unparalleled productivity. The benefits of welding automation extend far beyond mere operational efficiency. By entrusting welding tasks to automated systems, businesses mitigate the risks associated with human error, thereby safeguarding weld quality and minimizing rework. The resultant uptick in productivity translates to accelerated throughput and reduced time to market, a boon for companies operating in competitive markets. Furthermore, by alleviating workers from repetitive or hazardous welding tasks, automation plays a pivotal role in bolstering workplace safety. However, the journey towards welding automation is not without its challenges. Implementing automated solutions necessitates careful planning, strategic investment, and comprehensive training programs. Mpamac recognizes these hurdles and offers turnkey solutions that encompass everything from initial consultation and system design to installation, commissioning, and employee training. Their team of automation experts collaborates closely with clients, ensuring a seamless transition to automated workflows and maximizing return on investment. The evolution of welding automation often unfolds in incremental steps. For many companies, the initial investment may entail automated welding positioners, a fundamental building block that lays the groundwork for future advancements. As operations expand and demand grows, businesses may progressively incorporate more sophisticated solutions, such as column and boom manipulators, roller beds, and fully programmable robotic welding stations. The integration of advanced software facilitates offline programming, system-wide integration, and real-time monitoring, further enhancing operational efficiency and control. Embarking on the path to welding automation necessitates a collaborative effort involving management, frontline workers, and automation specialists. Every aspect of the process, from workflow optimization to equipment selection, is meticulously scrutinized to align with organizational objectives and operational requirements. With Pneumatic as a trusted partner, companies can navigate this journey with confidence, knowing that their transition to welding automation is not just an evolution, but a transformation that will shape the future of their operations. Welding trailer chassis involves a meticulous process that ensures structural integrity and durability, crucial for the safety and performance of trailers on the road. VOC Welding's arc welding robot solution for turbos Hoet in Belgium exemplifies a sophisticated approach to this task. The centerpiece of this welding setup is the Panasonic welding robot, strategically placed on a gantry system spanning a 16-meter track. This configuration allows for precise movement and coverage across the trailer chassis, ensuring consistent weld quality throughout the assembly process. Programming plays a vital role in orchestrating the robot's movements and welding sequences. VOC Welding utilizes DTPS offline programming software, enabling engineers to meticulously plan and simulate welding operations before implementation. This approach minimizes downtime and maximizes efficiency during actual production runs. The implementation of the automated welding line at Turbos Hoet was not without its challenges. Selecting the right supplier was critical, considering factors such as spatial constraints, service availability, and experience in handling large-scale projects. VOC Welding emerged as the ideal partner, offering a comprehensive solution tailored to the specific needs of the project. The benefits of this automated welding solution extend beyond efficiency gains. By eliminating manual welding processes, the risk of human error is significantly reduced, resulting in consistently high-quality welds. This not only enhances the structural integrity of the trailer chassis but also contributes to overall safety on the road. Furthermore, the modular design of the welding line provides scalability for future expansion. Additional workstations with robotic systems can be seamlessly integrated to accommodate increased production demands. This forward-thinking approach underscores VOC Welding's commitment to innovation and flexibility in meeting the evolving needs of its clients. Looking ahead, the future of robotics in trailer chassis production appears promising. By leveraging advanced technologies and collaborative partnerships, companies like Turbos Hoet and VOC Welding are poised to drive further advancements in efficiency, quality, and capacity within the industry. The Compact Robotic Beam Assembly, Welding, SBA Compact, is designed to streamline the process of assembling and welding structural beams, ensuring efficiency, accuracy, and safety. Here's how it works. Placing, loading of ADD parts. The process begins with the placement or loading of ADD parts onto the machine. These parts can include components such as H-beams, U-channels, tubes, angles, and plates. Scanning of ADD parts. Once the ADD parts are loaded, a scanning unit performs a full quality check of each part. This ensures that the parts meet the required specifications and are ready for assembly. Loading of beam. Simultaneously, the main profile or beam onto which the ADD parts will be assembled is loaded into the machine. This main profile can be a welded beam or a sin beam, as well as rectangular or square tubes. Assembly. The machine's tack and weld robot then takes over for fully automated and precise beam assembly. ADD parts are accurately positioned onto the main profile, preparing them for welding. Auto tool change. As the assembly progresses, the machine automatically changes tools as needed, ensuring a smooth workflow without manual intervention. Auto turning of ADD parts. An integrated profile turning device allows for the full 360 degrees rotation of beams, enabling maximum processing efficiency and continuous automated production. This feature ensures that all sides of the beam are accessible for assembly and welding. Welded beams and sin beams as main member. The welding process utilizes mag welding technology for both fillet and groove welds, ensuring strong and durable connections between the ADD parts and the main profile. Weld out. After assembly, the welded beams undergo further processes such as preheating to ensure optimal welding conditions and the automatic cleaning and recalibration of welding torches to maintain quality and consistency. Easy integration. The SBA Compact is designed for easy integration into existing workflows, allowing it to seamlessly become a part of your production process. Its modular design also allows for future upgrades to further enhance productivity. Welding and pipelaying are intricate processes that form the backbone of pipeline construction, facilitating the transport of energy resources across vast distances. Within this industry, pipelines, commonly referred to as mainlines, serve as critical arteries, ranging from 24 to 48 inches in diameter and spanning thousands of kilometers. The sheer scale and complexity of these projects demand precision and expertise in welding and pipelaying techniques. At the heart of pipeline construction are skilled pipeline journeymen and welders who employ a range of welding methods to join individual pipe sections. The choice of welding process depends on various factors, including the diameter of the pipe, the terrain, and project specifications. While manual welding methods require a high level of craftsmanship and attention to detail, automatic welding technologies have revolutionized large diameter pipeline construction, enhancing efficiency and consistency. Before welding can commence, meticulous preparation is required. Crews meticulously position and align individual pipes, ensuring they meet strict specifications and tolerances. In areas where laying a straight pipe is not feasible due to the terrain's contours, journeyman pipe layers, often referred to as stabbers, utilize specialized bending machines to shape the pipes accordingly. This process requires a keen understanding of geometry and material properties to achieve precise bends that align with the land's natural contours. Once the pipes are properly aligned, they undergo preheating to a specified temperature range to prepare them for welding. Preheating is essential for ensuring the proper fusion of the weld and minimizing the risk of defects such as cracking or distortion. The welding process itself involves multiple passes, each serving a specific purpose in ensuring the integrity of the weld joint. Beginning with a bead weld, welders work meticulously to deposit filler material along the joint, gradually building up layers to form a strong bond between the pipe sections. Throughout the welding process, welders maintain strict quality control measures, carefully monitoring parameters such as heat input, travel speed, and weld bead profile to ensure consistency and adherence to industry standards. In addition to manual welding methods, some pipelines employ advanced automatic welding technologies. These systems utilize robotic welding equipment controlled remotely by skilled operators. Automatic welding offers advantages in terms of speed, consistency, and quality, particularly in large-scale pipeline projects where efficiency is paramount. Beyond welding, pipelaying encompasses a range of tasks, including the installation of pipeline supports, tie-ins, and testing. Tie-ins, in particular, involve connecting finished pipeline sections to existing infrastructure, requiring precise alignment and welding techniques to ensure a seamless transition between segments. The P600 will be operated onboard Helix SG's pipelaying vessel Caesar. The process begins in the ship's massive pipe hold. Crane operators load pipe onto the rollers. Rollers move the pipe between stations. The pipe is rollered onto the pipe elevator. The pipe arrives on the production deck. And is rolled into the pipe facing station. Where the pipe ends are beveled for mechanized welding. The pipe is positioned for the pipe-facing machine ORPFM. The PFM is inserted into the pipe. The operator engages the faceplate. When the bevel is finished, the PFM is removed from the pipe end. The pipe ends are now beveled and ready to be welded. The pipe is now moved to the bead stall. Before the pipe can be welded, it must be preheated. The pipe is moved into the preheat area. The band is put on the pipe and adjusted to a predetermined distance. The pipe is heated to the qualified temperature to evaporate all moisture from the surface. After preheat, the pipe is moved to the firing line. The reach rod is inserted into the next piece of pipe. The clamp is aligned and the spacer signals for the next piece of pipe. When the pipe ends are aligned, the spacer taps the pipe. The reach rod operator raises the clamp's shoes and clamps the bevel in place. Helpers place the P600s on the pipe band. The welder deposits the root and hot passes. The second weld station fills out and caps the pipe. The finished weld is tested with X-rays. Film is wrapped around the weld. The X-ray bug is activated via the isotope and emits X-ray for 15 seconds. The journey from raw materials to steel is a global endeavor. These raw materials are transported by ship and rail, converging at the production hub. The transformation begins with the processing of iron ore into concentrated iron ore pellets. These small spheres are convenient for transport, storage, and processing. Within the sprawling steel production facility, several towering blast furnaces, some as tall as 15-story buildings, work tirelessly, churning out up to 14,000 tons of pig iron daily. The process commences as coke and ore are conveyed to the blast furnace, alternating layers by means of a rotary chute. As the layers descend, rising processed gas, generated by preheated air at 1,200 degrees Celsius, initiates the reduction and melting of iron ore. This arduous process, taking 8 hours, culminates in liquid iron and slag in the lower part of the furnace, with periodic tapping every 2 hours. At around 1,450 degrees Celsius, the pig iron and slag are forcibly discharged through the tap hole and immediately separated. Samples are taken to assess quality, a task performed by professionals donned in protective gear. Below, torpedo ladle cars, named for their elongated shape, await their payload. The scale of the steel mill at Skeeter Flash Star is awe-inspiring, spanning over 400 meters in length, a space vast enough to accommodate nearly 480 detached houses. The next phase sees pig iron poured from torpedo ladles into transport ladles, each holding approximately 200 tons. Scrap is introduced into the process alongside pig iron, both converging in a converter. At Skeeter's site, there are 3 LD converters utilizing technically pure oxygen through porous plugs and an oxygen lance. The intense heat further refines the molten pig iron while removing unwanted elements, known as carbon drop. Although temperatures can theoretically reach 3,000 degrees, they are controlled to around 1,700 degrees by the introduction of chill scrap. This converter process, lasting approximately 40 minutes, transforms pig iron into crude steel, with each converter boasting a capacity of 220 tons. The site produces up to 12,500 tons of crude steel daily. Yet, steel is not a one-size-fits-all material. Depending on its intended purpose and customer requirements, alloying elements such as manganese, silicon, chromium, nickel, titanium, and molybdenum are added to the crude steel at the VPL plant to create specialized, high-grade steel. These distinct steel grades are then directed to continuous casting lines that fashion them into slabs from the molten steel. These slabs develop a solid outer shell while the core remains molten. The slabs are subsequently torch cut into manageable pieces for shipment. These slabs, some as thick as 35 centimeters and weighing up to 32 tons. The hot rolling process is responsible for transforming steel slabs into a wide range of products, including sheets, plates, and structural components. It involves a series of precisely controlled steps that impart strength, shape, and desirable properties to the steel. Heating. The process begins with heating steel slabs to extremely high temperatures, often exceeding 1,200 degrees Celsius. This intense heat softens the steel and makes it more malleable, preparing it for deformation. Rolling. The heated slabs are then fed through a series of rollers within the hot rolling mill. These rollers gradually reduce the thickness of the steel while also shaping it according to the desired specifications. As the steel passes through the rollers, it undergoes significant mechanical pressure, which refines its grain structure and enhances its strength. Cooling. After the rolling process, controlled cooling is often applied to the steel. This controlled cooling can be achieved through various methods, such as air cooling or water quenching. Cooling is essential for stabilizing the steel's properties and preventing deformation. Sizing and inspection. The rolled steel undergoes further processing, including sizing and inspection. This stage ensures that the steel meets the precise thickness and dimensional requirements specified by customers. Quality control measures are in place to identify and rectify any defects or deviations. Experienced operators oversee the entire process, ensuring precise control over temperature, pressure, and rolling speed. Modern technology, including data networks and automation, plays a crucial role in monitoring and optimizing the mill's performance, ensuring consistency and efficiency. Walter Tosto Spa, located in Italy, has established itself as a global leader in the manufacturing of high-pressure equipment and vessels, with a strong reputation for quality and precision. One of the key assets in their production process is a state-of-the-art robotic welding system. This system boasts an impressive ability to coordinate 8 axes simultaneously, ensuring unparalleled precision with a repeatability of 0.1 millimeters. The robot's load-bearing structure is ingeniously designed to minimize bending, even at maximum extension, ensuring the highest quality welds. Its large work area allows for flexible arrangements of pieces, facilitating circular welding around the beam. Additionally, the facility features a Correa Versa gantry milling machine, equipped with 5 axes. This advanced machine can handle pieces up to 10.5 meters in length, 1.65 meters in height, and 6.8 meters in width, all while maintaining exceptionally tight tolerances. Furthermore, the company has invested in 5 furnaces for heat treatment operations, each tailored for different sizes, temperatures, and thermocouple needs. With an extensive machine park and cutting-edge technologies, the facility has the capability to conduct all critical activities in-house, ensuring that every high-pressure equipment and vessel they manufacture meets the highest standards of quality and reliability. At Goodwin Steel Castings, the production process of a steel casting begins with the meticulous creation of the casting mold. This step is absolutely critical, as it defines the final shape and characteristics of the steel casting. The foundry's skilled craftsmen excel at crafting molds tailored to exacting specifications, accommodating a wide range of applications. The company's expertise extends to handling high alloy and nickel alloys, allowing them to meet specialized requirements within industries like power generation. Following mold preparation, the foundry experts move on to the melting process, a stage where precision is paramount. Their distinction lies in its ability to work with a diverse array of alloys, including the historic achievement of producing the world's first MAR-BN 9% CR steel, casting for advanced ultra-supercritical power generation. During this phase, strict control over alloy composition and temperature is maintained to ensure the desired material properties are achieved. The company's groundbreaking research and development efforts have yielded remarkable advancements in steel alloys. For instance, the development of the G130 grade has expanded the possibilities for heavy section castings, particularly in applications where turbines operate above 700 degrees Celsius. This innovation has extended the section size limitations of super duplex stainless steel castings while simultaneously enhancing corrosion and impact resistance, making it an ideal material choice for a broad spectrum of applications. The company's machine shop represents the pinnacle of advanced manufacturing, featuring state-of-the-art CNC machining and inspection facilities. These CNC machines aren't just tools. They are precision instruments used to refine and shape castings to exacting standards. The intricate and precise machining carried out at machine shop is essential to meet the stringent requirements of industries such as power generation. The welding stage plays a crucial role in enhancing the strength and durability of castings, especially in applications subjected to high levels of stress. This machine shop offers a diverse range of welding processes, including robotic overlay welding of hard facings and nickel-based cladding. These processes contribute to the resilience and longevity of the castings. Furthermore, the machine shop employs various welding methods such as GMAW, FCAW, and SAW for both manual and robotic welding, ensuring flexibility and adaptability to meet diverse customer needs. Quality control is a paramount concern at here. Rigorous testing procedures are conducted to ensure that the castings meet and exceed the required standards. The company employs both destructive and non-destructive testing methods to scrutinize properties such as corrosion resistance, impact resistance, and structural integrity. Cutting-edge equipment like scanning electron microscopes equipped with spectrographic EDX are employed for in-depth metallurgical analysis, ensuring that the highest quality is maintained throughout the manufacturing process. Goodwin's capabilities extend to assembling complex product assemblies, some weighing up to an astounding 100,000 kilograms. This final step showcases the company's unparalleled ability to handle massive and intricately designed components, delivering end-to-end solutions to its customers. The forging process for large long shaft forgings is a critical aspect of heavy equipment manufacturing, as these forgings serve as core components in machinery and equipment. The quality and performance of these forgings are of utmost importance due to the heavy loads and complex operations they endure. To meet these stringent requirements, the free forging process has been developed and optimized to reduce production costs, energy consumption, and improve forming quality. Large long shaft forgings play a pivotal role in heavy equipment manufacturing, serving as transmission shafts and key components. Given their critical role, these forgings must meet extremely high quality standards. The production process for large long shaft forgings involves several stages, including pre-forging heating, the forging process itself, and post-forging heat treatment. Due to the complexity of production, various factors come into play, necessitating the development of a rational free forging process to ensure the safe heating of the ingot, reduce heating time, save energy, and meet the necessary heat treatment requirements. The significance of large long shaft forgings lies in their installation in critical parts of machinery and their exposure to heavy loads. Consequently, these forgings must be free from defects such as porosity, segregation, and inclusions to achieve the required performance. As these forgings are typically made from ingots, which inherently contain metallurgical defects, addressing these defects becomes essential. This involves eliminating the metallurgical defects of the ingot itself, achieving a uniform fine grain structure, and ensuring a quantitative distribution of mechanical properties in the forging. The quality of these forgings not only drives industrial development but also ensures the safety of equipment operators. The free forging process offers several advantages over traditional forging methods. It employs simple tools and offers greater flexibility and versatility, which can rectify the shortcomings of traditional forging techniques. By improving the free forging process for large long shaft forgings, it becomes possible to obtain uniform fine grain structures, shape the forgings as required, and reduce or eliminate internal defects in the ingots, thus enhancing the overall performance of these forgings. The heating process is a critical aspect of large long shaft forging production. It involves pre-forging heating, forging, and post-forging heat treatment. Given the single-piece production nature of large forgings, any rejection or scrapping of forgings can result in significant economic losses and construction delays. Therefore, it is imperative to establish rational heating specifications that ensure the safe heating of steel ingots and minimize heating time, thus contributing to energy conservation. The optimization of heating specifications involves careful consideration of temperature and stress fields within the steel ingot during heating. The goal is to achieve rapid and efficient heating while minimizing stress, especially at the core of the ingot. Parameters such as insulation temperature and time during the phase change period are critical for achieving efficient heating. Additionally, the choice between low temperature and high temperature charging methods must be made while controlling the highest charging temperature to prevent adverse effects on the forging. The automatic welder revolutionizes storage tank welding with its versatile functionality and advanced features. Designed for horizontal welding outside the tank, it boasts magnetic fixation, allowing it to securely adhere to surfaces in all positions. Equipped to handle MIG-MAG, tubular wire, and TIG processes, the automatic ensures adaptability to diverse welding requirements. Its key benefits include heightened productivity through increased welding speed and material deposition, enabling continuous operation with minimal interruptions. Moreover, the automatic prioritizes quality, offering precise control over welding process variables and execution parameters. This results in a significant reduction in rework, enhancing overall efficiency and product integrity. Safety is paramount with the automatic, ensuring absolute operational safety for welders. Its ergonomic design promotes comfortable body positioning away from critical welding zones, enhancing user comfort and reducing fatigue. Pipeline welding is a critical aspect of constructing and maintaining the vast network of pipelines that transport fluids or gases over long distances. Whether it's for oil, natural gas, water, or other substances, ensuring the integrity and longevity of pipelines is paramount for safety, efficiency, and environmental protection. Understanding the properties of the materials being welded is essential. Pipelines may be constructed from various materials such as carbon steel, stainless steel, or alloy metals, each with its own welding requirements and challenges. It's crucial to ensure that the materials meet the specifications outlined in the welding procedure and adhere to industry standards and regulations. Developing a comprehensive welding procedure specification, WPS, is essential. This document outlines the specific welding parameters, techniques, and inspection requirements for the pipeline project. Factors such as pipe diameter, wall thickness, material type, welding position, and environmental conditions should be considered when drawing the WPS. Adherence to revised welding codes and standards such as those provided by the American Welding Society, AWS, or the American Petroleum Institute, API, is imperative. Qualified welders play a crucial role in ensuring the quality and integrity of pipeline welds. Welders must undergo certification and qualification procedures in accordance with applicable standards. Qualification tests should assess a welder's proficiency in various welding techniques, positions, and materials relevant to the pipeline project. High-quality welding equipment and consumables suitable for pipeline welding applications should be used. Welding machines must be calibrated and maintained regularly to guarantee consistent performance. Appropriate welding consumables, such as electrodes or filler wires, should be selected based on the material being welded and the welding process employed, e.g., shielded metal arc welding, gas tungsten arc welding. Thoroughly cleaning and preparing the welding area, including the pipe surfaces and joint interfaces, is crucial to remove contaminants such as rust, oil, dirt, and moisture. Proper fit-up and alignment of the pipes should be verified to minimize welding defects and distortion. Measures to prevent heat-affected zone, HAZ, contamination, such as purging inert gas into the pipe interior during welding, should be implemented. Welding techniques that ensure proper penetration, fusion, and deposition of weld metal while minimizing effects such as porosity, lack of fusion, and undercutting should be employed. Maintaining appropriate arc length, travel speed, and electrode angle throughout the welding process is essential to achieve uniform and sound welds. Welding parameters should be adjusted based on the joint configuration, material thickness, and welding position to optimize weld quality. Implementing post-weld heat treatment, PWHT, if required to relieve residual stresses and enhance the mechanical properties of the weldment is essential. Visual and non-destructive testing, NDT, inspections, such as radiographic testing, RT, or ultrasonic testing, UT, should be performed to evaluate weld quality and detect any defects or discontinuities. Surface cleaning and finishing operations should be conducted to remove weld spatter, slag, and any other surface imperfections. Adhering to safety protocols and procedures to protect personnel, equipment, and the environment during welding operations is crucial. Mitigating potential hazards such as fire, explosion, and toxic fumes by implementing appropriate ventilation, fire prevention measures, and personal protective equipment, PPE, is imperative. Considering environmental factors such as temperature, humidity, wind, and altitude, which can affect welding performance and weld quality, is also important. Maintaining accurate records of welding activities, including WPS documents, welder qualifications, inspection reports, and material certifications, is essential. Ensuring traceability of materials and welding consumables to verify compliance with specifications and regulatory requirements is crucial. Facilitating comprehensive documentation for auditing purposes and future reference during pipeline maintenance and integrity assessments is imperative. The largest and most efficient steel beam assembler, SBA, stands as the crown jewel of every automated steel factory. A marvel of engineering, it combines power, precision, and unparalleled efficiency to revolutionize the fabrication process. Let's delve into the intricate workings of this machine, exploring its design, capabilities, and the significant rewards it brings to manufacturers. Power and precision. Imagine a single worker overseeing the SBA Conti line, orchestrating a symphony of automated processes that churn out steel beams with remarkable efficiency. In an 8-hour shift, this machine can process an impressive 13 beams, a feat that surpassed even the lofty expectations of a customer in Japan. Design. Customization lies at the heart of the SBA Conti line. Each unit is meticulously tailored to the specific needs of the manufacturer, ensuring seamless integration into existing workflows. From in-feed systems with automatic beam straightening to built-in features designed to handle the toughest jobs, this machine dares fabricators to challenge its capabilities. Crafted with precision in Austria, the SBA Conti boasts outstanding attention to detail. Its design accommodates various plant setups, catering to facilities with continuous material flow and high output demands for welded structural steel. Whether you opt for the standard SBA Conti or the enhanced SBA Conti Plus with additional welding robots, rest assured that every component is engineered for maximum efficiency and reliability. Investment and reward. Investing in a steel beam assembler promises rapid returns. Beyond the financial benefits, the SBA Conti prioritizes worker safety, reducing downtime associated with injuries on the job. Automation not only accelerates production but also enhances accuracy, mitigating the risk of errors that lead to delays and injuries. With machines that never tire, manufacturers can confidently meet deadlines and boost profitability. Technical specifications. The SBA Conti is equipped with a suite of cutting-edge features designed to streamline the assembly process. Highest automated line. Incorporates automatic in-feed and unloading systems for main profiles, ensuring continuous operation. Laser measurement. Accurately defines material dimensions and locates the zero reference point, laying the foundation for precise assembly. Tack and Weld Robot enables fully automated beam assembly, complemented by up to 4 welding robots in the double-line configuration. Parts Scanning Unit conducts comprehensive quality checks on all additional parts, ensuring adherence to exact specifications. Parts Robot positions additional parts with pinpoint accuracy, facilitating seamless integration into the assembly process. Integrated Profile Turning Device enables full rotation of beams for maximum processing efficiency and continuous production. Profile Clamping Unit secures main profiles during tack and welding operations, maintaining stability and precision. Machine Control offers full automation with comprehensive data monitoring and control from a safe distance. Profit Software facilitates semi-automated generation of assembly and welding workflows, optimizing efficiency and reducing human error. The advent of fully automated tracking and welding of steel beams marks a significant milestone in the structural steel fabrication industry. Robotic welding, assembly, and fabrication have long been seen as the future, promising increased efficiency, precision, and cost-effectiveness. Now, with innovations like Siemens' SBA, steel beam assembly, technology, this future has become a reality, transforming the conventional steel fabrication market. The SBA technology represents a true game changer in steel fabrication, addressing past challenges and hurdles unique to the industry. For many years, the idea of robotic assembly and welding of structural beams seemed distant in an industry characterized by traditional, lot-by-lot, production methods. However, the SBA technology has shattered these preconceptions, ushering in a new era of efficiency and productivity. The reliability and efficiency of modular concepts in robotic steel beam assembly and welding have been attested to by satisfied clients, with repeated orders serving as evidence of its success. There is a range of robotic assembling and welding lines, each designed to optimize production capacity and efficiency. These systems boast impressive features, such as the ability to assemble add-on parts in less than 1.5 minutes per part, regardless of weight. The integration of ProFit software enables seamless 3D data flow to the robots, eliminating the need for programming or robot teaching. Comparative efficiency measures highlight the superiority of robotic welding over manual methods, with arc on time reaching 65% for robotic welding systems compared to 20 to 25% for manual welding. The SBA modular concepts are designed to accommodate various client requirements, including floor space limitations, existing material flow considerations, production capacity goals, and budget constraints. These modular systems offer flexibility, allowing for easy setup, extensions, and upgrades to meet evolving production needs. The radial-axial ring rolling machine is a remarkable piece of industrial equipment known for its precision and efficiency in producing seamless rings of various sizes and materials. Let's delve into how this machine operates and why it is highly regarded in the manufacturing world. The process begins with the production of a ring blank. Specialized presses are used to create these blanks, typically from cylindrical or rectangular billets of metal. These blanks are initially oversized to account for the material that will be displaced during rolling. The ring blank is heated to a specific temperature to make it more malleable. The heating process typically consumes a significant portion of the energy used in ring rolling. Once heated to the right temperature, the blank is placed onto the radial-axial ring rolling machine. There are two primary rolling methods, radial and radial-axial. In the radial method, the blank is rotated as it's compressed between two rollers. In the radial-axial method, an additional axial force is applied to elongate the blank while it's being rolled. This elongation allows for the production of rings with a more pronounced height. Advantages of the radial-axial ring rolling machine. Energy efficiency. One of the standout features of this machine is its energy efficiency. Precise rolling, aided by sophisticated control systems, minimizes material wastage and reduces energy consumption during the heating phase. High precision. The laser measuring systems and advanced control technology ensure that the rings produced have tight tolerances and meet stringent quality standards. Material versatility. The radial-axial ring rolling machine can work with a wide range of materials, from carbon steel to superalloys, providing manufacturers with flexibility in their production processes. Cost-effective production. The combination of energy efficiency, precise rolling, and material versatility results in cost-effective production, as it reduces the need for excessive material, machining, and energy consumption. During the rolling process, precise measurements are crucial. Many machines are equipped with laser measuring systems that continuously monitor the outer diameter of the ring. This data feeds into a control system that adjusts the machine's parameters to ensure the final product meets the desired specifications. The rolling process shapes the blank into a ring, but it may not achieve the exact final dimensions and tolerances. Additional machining or heat treatment may be necessary to achieve the desired properties and dimensions. HGG Group's large diameter pipe cutting machine is specialized tools designed for the precision cutting of large diameter pipes, particularly in industries like offshore construction. This machine plays a pivotal role in ensuring the quality and accuracy of pipe-to-pipe connections and are known for their efficiency and versatility. Cutting technology. Large diameter pipe cutting machines utilize advanced CNC, computer numerical control, technology to execute precise cuts on large pipes. They can accommodate pipes with diameters ranging from 50 millimeters, 2 inches, to a substantial 8,000 millimeters, 26 feet, and varying wall thicknesses, making them suitable for a wide range of applications. Data input. To initiate the cutting process, Operators input either 3D CAD files or 2D drawings of the desired pipe sections and connections. These machines are compatible with various industry standard formats, ensuring flexibility in data preparation. Data processing. Once the data is provided, the large diameter pipe cutting machine software processes it to determine the optimal cutting path and parameters. This step involves generating NC, numerical control, data, which serves as instructions for the machine's cutting head. Cutting precision. The cutting head of the machine is equipped with specialized cutting tools that can execute a variety of bevels, including V bevels, Y bevels, K bevels, and X bevels. These bevels are crucial for welding preparations and ensure that the pipe-to-pipe connections are made with precision and reliability. Transportability. These machines are designed for transportability, making them suitable for on-site cutting. They can be easily transported to the location, eliminating the need to transport large pipes to a central cutting facility. This feature significantly reduces logistical complexities and costs associated with large-scale construction projects. The 2-ton Hydra-Pneumatic forging hammer is an innovative and highly efficient forging tool that has revolutionized the metalworking industry. Developed by Forge Tech Services Limited in the UK, this hammer is an upgraded version of the 1.5-ton Massey Rigby type hammer, now boasting a 2-ton capacity. Its operation is based on a combination of hydraulic power, nitrogen, and advanced cooling systems, making it a powerful and environmentally friendly choice for forging processes. At its core, the Hydra-Pneumatic forging hammer utilizes hydraulic power to provide the lifting force required for the forging process. This hydraulic force is responsible for raising the hammerhead to the desired height, allowing it to be positioned precisely over the workpiece. Once in position, the hammer utilizes nitrogen as the blow motive force. Nitrogen is an excellent choice for this purpose as it offers a high degree of controllability and can deliver powerful blows to the material being forged. One of the standout features of this hammer is its air or water cooling system. The cooling system helps maintain the hammer's efficiency and prolong its lifespan. It prevents overheating, ensuring consistent performance even during prolonged use. This cooling system also contributes to the hammer's high blow rate, allowing for rapid and efficient forging of materials. The Hydra-Pneumatic forging hammer is known for its superior control. Operators can precisely adjust the force and speed of each blow, making it suitable for a wide range of forging applications. This level of control results in high-quality finished products with minimal waste and rework. One of the most significant advantages of this hammer is its energy efficiency. Unlike traditional forging hammers that rely on compressed air, the Hydra-Pneumatic forging hammer offers a groundbreaking approach to energy consumption that sets it apart as a remarkable advancement in the field of metalworking. Traditional forging hammers primarily rely on compressed air to generate the force required for forging operations. While compressed air has been a staple in manufacturing for many years, it has some inherent drawbacks. The compression and storage of air can result in significant energy losses, especially when considering the conversion of electrical energy into compressed air and the subsequent release of that energy during the forging process. This inefficiency can lead to increased operating costs, higher energy bills, and a larger carbon footprint. Ring rolling is a manufacturing process used to produce seamless, circular rings with a variety of diameters and cross-sectional shapes. This process is commonly employed in industries to create parts like bearings, flanges, and gears. Ring rolling machines play a crucial role in this process, enabling the transformation of raw materials into precise and durable ring-shaped components. Here's how a ring rolling machine works. The heated material is placed in the ring rolling machine, where it is positioned between two main rollers. One roller remains stationary while the other is driven by a powerful hydraulic or mechanical system. The roller's axial feeding mechanism moves the material closer to the forming area. As the material is gradually fed into the rolling machine, the main rollers exert both axial and radial pressure on it. The axial pressure reduces the height of the workpiece, while the radial pressure causes it to expand outward, forming a ring shape. This process continues as the rollers rotate at precise speeds to achieve the desired dimensions and thickness. In some cases, an additional mandrel or idler roll may be used inside the ring to maintain its internal diameter and provide greater control over the shape and dimensions. This can be particularly important for achieving tight tolerances and ensuring the finished ring meets the required specifications. After the ring reaches its desired dimensions and shape, it is usually cooled to prevent deformation and maintain its structural integrity. Cooling methods can include air or water quenching. Additionally, the finished ring is inspected for any defects or imperfections to ensure quality and accuracy. Ring rolling machines come in various sizes and configurations to accommodate a wide range of ring sizes and shapes. The process offers several advantages, such as reduced material waste, enhanced mechanical properties, and the ability to create complex geometries. It is a versatile and efficient method for producing high-quality rings used in diverse industrial applications. At Great Wall Steel Casting, the manufacturing process of slag pots involves several key steps, with most operations taking place in-house at their foundry plant. Here is an overview of the process. Molding. Sand molds are used to shape the slag pot. The exact dimensions and design are based on engineering patterns. Trunnions. If required, trunnions are cast into the slag pot. These trunnions are typically made from S355 J2G3 steel to meet DIN N102502 standards. Melting. The melting process occurs in the oxygen steel plant. The ladle has a capacity that allows for a continuous bottom pouring process, which is continuously monitored for speed and quality. Metal analysis is performed using a computer-linked spectrograph to ensure the right composition. Heat treatment. The slag pot undergoes heat treatment, which includes heating to a temperature above AR3, austenitizing, at around 915 degrees Celsius. Controlled cooling in a furnace is then followed by an intermediate holding phase at 600 degrees Celsius to 630 degrees Celsius. The cooling process continues in the furnace until the temperature reaches 300 degrees Celsius. Fettling and dressing. The inner surface of the slag pot is carefully processed to remove surface discontinuities that could cause slag to stick. Additionally, the castings are descaled using shot blasting. The exterior of the slag pot is coated to protect it during transportation. This comprehensive manufacturing process ensures the production of high-quality slag pots that meet the required standards and are ready for use in various industrial applications. The production of the reactor plant for the newest nuclear-powered icebreaker. The process begins with the casting of blanks, which are the starting materials for various components of the reactor plant. These blanks weigh a total of 547 tons and are subjected to extreme heat, reaching temperatures of up to 1200 degrees Celsius. This high-temperature forging is essential to create the strong and durable components required for the icebreaker's reactor. Machining of flange holes. One of the most challenging tasks is machining the flange holes for the steam generator cassettes. It takes 39 hours to machine just one hole, involving 38 meticulous steps and specially developed tools and processes to achieve the required accuracy. Corrosion-resistant surfacing. A total of 10 tons of corrosion-resistant tape is applied to safeguard the metal surfaces. This surfacing process spans over 8 months and adds an additional layer of protection to the reactor components, ensuring their longevity. Making the girth weld. The girth weld is a critical component that holds the reactor vessel together. It requires 4 days of continuous welding, using an impressive 600 kilograms of molten metal wire. The thickness of the weld measures 150 millimeters. Welding the nozzles and heat treatment. To ensure their durability and integrity, they undergo a meticulous welding process. The metal is preheated to 200 degrees Celsius before welding to prevent cracks in the welded joints. This process takes 3 days to complete. Closing weld. Joining the semi-vessels into a single, cohesive unit is a critical step in assembling the reactor plant. This process requires 600 kilograms of molten metal wire and results in a weld with a thickness of 150 millimeters. Welding the hydraulic chambers. Each hydraulic chamber, with a substantial weight of 4,500 kilograms, undergoes a 20-day welding process. Welds with a thickness of 82 millimeters are meticulously crafted. These hydraulic chambers play a vital role in the operation and control of the reactor plant. Fabrication of in-vessel internals and reactor closure head. The intricate components inside the reactor vessel, such as internals and the reactor closure head, are fabricated with precision. These components are designed to ensure the safe and efficient operation of the nuclear reactor within the icebreaker. The production of the reactor plant for the newest nuclear-powered icebreaker is a testament to the expertise, dedication, and innovation of the team at Atomenergomash. This nuclear heart powers the icebreaker through the harshest of Arctic conditions, allowing it to navigate frozen waters and maintain a strong presence in this challenging environment.